All right. So let me talk first about this internal so you guys know what to expect. It is currently getting checked off by one of my chemistry teacher friends to make sure that it is a fair assessment, but it should be fine. So what my plan is for the assessment is to give you guys 4 different molecules to identify. With those 4 different molecules that I want you to identify, the grade is going to be based off of your best 2. So if you muck up 2, you're fine. Since I'm doing the best of your 2 identifications, what I'm going to do is I'm going to give you the first 2 molecules. I will mark it, and I will give you feedback. If you are happy, like let's say your first 2 molecules you got merit and excellence, then your overall grade will be a merit. If you are happy with a merit, then you can use the next session, whenever the rest of the class does the other 2 extra molecules, you can use that as tutorial time. Okay? If you are not happy with your grade from the first 2 questions, let's say you got merit and excellence and you want to get an excellence overall, then I can give you another 2 molecules and that gives you 2 more chances to get 2 excellence ones. So 2 molecules, feedback, and then a second 2 molecules making up 4. So if you are happy, let's say the first time you were really good at it, you got excellence and excellence, your overall grades and excellence, then you're done. You don't need to do 2 more molecules for me. Does that sound like a good, fair thing? I'm trying to make more of my assessments portfolio based instead of just like sit and do a test. And normally what I would do is have like a formative practice and then an actual final one. And I'm like, why am I doing that? I can just give you guys a formative, use that as evidence, and if it's fine, then we don't have to do the second one. So that's how I organize the assessment. Are you okay with that so far? All right. There are going to be 2 different ways I ask the question. Wait. There are going to be 2 different ways I ask the question. The first way I ask the question is I give you basically a blank canvas. So I won't give you any information about the molecule. I'll just give you the 3 spectra, and I'll ask you to figure out what it is. That's one of the little harder ones. Actually, I don't know if the other one's necessarily harder or easier. The second version I will give you is like question number 5. Same thing. I give you 3 spectras, but I give you a hint to help you out. So I say, for example, the empirical formula of this compound is C2H0. So that's obviously not the molecular formula, because molecular formula, because I say it's empirical. So molecular formula, remember, is referring to the full molecule with its everything that it's supposed to have. Empirical is the simplified version. The reason why I give you this formula is 2 things. First off, it gives you a little bit of a hint. Secondly, it also helps hint to you what functional group it might be. So either maybe I have 2 functional groups and I have like a dichloro, or I have something that has multiple of 1. So for example, if I have multiple oxygens, the 2 molecules that have multiple oxygens are carboxylic acid and esters. Esters are kind of really hard to determine on the data that's given to you because the only thing you can really see is the carbonyl. It's really hard to see that single bonded oxygen component. So to help hint that you have an ester, I give you the empirical formula for that. Does that make sense so far? So with question number 5, for example, I've given you the empirical formula, and the answer is going to be some ratio of it. So maybe times 2, times 3, times 4. Most likely times 2, because if you have 1 oxygen, you times it by 2, then you have enough for ester or carboxylic acid. So usually if I give you an empirical question, it's usually a hint that it's going to be carboxylic acid or ester, or it'll be some sort of di something. Okay? Are we okay with that so far? So 2 different versions. The one that I'm going to do as my teaching example is going to be the blank canvas version, where I've given you no information whatsoever, and you have to figure it out from that kind of component. So what I'm going to do is I'm going to go through and label stuff for the achieved to show you what you need to do as a bare minimum, and then I'll go through and add the merit level answer and then the excellence level answer. Are we good? All right. So for the achieved, all you need to do is identify information on the spectra. So for example, I identify that this here is my CH because that is what I'm using as my reference point. The other thing I can identify is that this here is my NH. And that is my primary because I realize there's two peaks. The other thing I could recognize is that when I look at 1700, that is not a typical carbonyl peak because it's too short. So I can write down there's no C double bond O. Now for the achieved, I don't need all of that. I just need you to show me at least one component to show me you know how to use IR. So it's basically a huge kind of OR option. Tell me it's primary, or you can tell me what it is, or there's lots of just ORs. Does that make sense? Sorry, I'm putting the ORs down there. So you don't need everything for the first. All right, the next thing then for achieved is I need you to figure out how many carbon environments there are. 1, 2, 3, 4. So you say there's 4 carbon environments. The other thing that I'm happy to accept as my OR option is if you tell me what the different peaks are. So basically identifying that that would be your amine peak. Let me just grab my periodic table and my sheet here. So when I'm looking at the spectra for the CMMR, if I have a carbon attached to a nitrogen, it should be between 37 and 45. This one here is actually a little bit higher, and that's why I'm saying you're better off using the IR. But when I'm looking at that CMMR, this one here is probably that carbon with the nitrogen. So again, it's an OR option, so long as you can tell me something. I just need to see that you can take data from the spectrums. Does that make sense? All right. Last thing on here then is my mass spectra. And I don't think I've labeled this one, which is a little annoying because I need to now figure out how many it is on there. I'm pretty sure, what was it? CH3, 30. All right, so you can't see it on there, and that was my bad for not printing it. The molecular ion on there, so this one is really tiny, so I would have labeled it. So apologies for not labeling it. It's actually at 73, 1, 2, 3, that peak there. So that one's really hard to see. I would have labeled it. I forgot to label it on there for you. 73. I forgot to provide that. So it's really tiny, so I will give that to you. Yeah, because that was my bad. Yeah, so you know how I was saying in some of these questions, I do label the molecular ion because it's too small. Did I forget to do it on all of these? Yeah, I did. No, I'm sorry. Oh, that's not nice. I forgot to label it on all of them. All right, I'll double check and go through and see if you need it labeled for the other questions. Okay? So, again, for the achieved, what I need you guys to identify is the molecular ion. So you'd say that that there is the molecular ion. Equals the 73 mass to charge ratio, or you tell me that that's the base peak. And that base peak is at 44. So again, it's a nice little OR option. So for the achieved, you don't even need to get all the things labeled. I just need to see that you understand the basics of like what information you can pull. Are we good so far? All right, keep going. All right. So let's go to the merit now. So for a merit, so I'll just write that down. That's an achieved level answer is what's in red. What I'll add in blue is the merit. So obviously I've done all the achieved requirements. I'm going to go through now and build it up to a merit level. So to build it up to a merit level, the main thing I want to do is be able to identify the molecule. So you need to identify all the components to it. So instead of this being an or an or option, this is now an and. So you need to have all of them. Same thing with the carbon environments. I need to mention the carbon environments, and I need to identify that that is the CN peak. So again, it's not an and, or sorry, it's not an or anymore, it's an and. Are we good so far? All right, all of this information together, I should be able to pull and decide that therefore I'm dealing with an amine. And it is a primary one as well. Cool? All right. Now, what I need to do is figure out what molecule I have from all that information. So with my molecular ion, if you guys remember, I suggest you draw just an N carbon with the amine, like that, and figure out the number. So I have nitrogen on the periodic table, which is going to be my 14. I have 2 hydrogens, so that's plus 2. Carbon is 12, and another 2 from the hydrogens. So that is going to be a 30. Now we're going to play the game of add 14 until I'm 1 away. So 30, if I add 14, I'd be at 44. If I add another 14, I'd be at 58. If I add another 14, I would be at 72, and then I add that extra carbon at the end, and that gets me to 73. So how many carbons are in here? 4. 1, 2, 3, 4. Are we okay with that? All right. Yeah, you just keep adding it till you're 1 away. So that way you figure out how many carbons there are. All right, we good? So now I need to draw some molecules that fit the parameters of 4 carbon environments, amine, and a primary amine. So for example, I could do I could do a straight chain with a nitrogen at the end. Does that meet all the parameters? 4 carbon environments, amine, primary amine, and meets all the parameters. Is that the only one that meets all those parameters? No. So what else could I do? I can move that amine down. So I'm doing this in green because that's actually the correct answer, and I'll explain why that's the correct answer. Does that meet the parameters? Y'all just shaking your head no. Why do you think no? Don't know how to communicate it? It's got 4 carbon environments. It's a primary amine and same molecular ion weight. So these 2 are both appropriate answers. Are there any other isotopes that would fit those parameters, you think? What happens if I branch it? If I did like a 3 carbon chain with an amine and a branch off of it. You want me to draw it so you guys can see it? Yeah. All right, so let's say, for example, I do CH3C, CH3, NH2, CH3. So that one's only 2 carbon environments, so I know that one's out. Do you see, guys, how to kind of show your working? Yeah, they're not so far apart, so that suggests to me it's this one. And then we're going to look at the fragments, because the fragments will tell me for sure. So a merit level student will give me this answer, because it does fit the parameters, but it's not the right answer. All right, the other thing a merit level student will do is they'll talk about fragmentation, and they'll be able to identify one of the fragments. So for example, we know what 30, actually let's do, let's see, just trying to think which one would still work. Okay, so 15 plus 14. So I should have a peak at 29. So if you're going for the merit, you'd go, oh, the 29 peak is CH3CH2 plus, and that's my 29 mass to charge. So a merit level student will tell me at least one fragment. Are you okay so far?
Is that correct?
That is correct.
Oh, okay.
It fits also with the excellence, because you see how both of these molecules are the same.
Yeah.
You'll be able to get a CH3, CH2.
Yeah.
All right. So a merit level student will be able to give me all the information. They'll be able to identify a molecule that fits the parameters but may not be perfect for the answer. And they'll also be able to figure out a fragment and tell me it. All right. Shall I show you what to do for excellence and why it's this molecule and not that one? All right. So the stuff in blue is the merit. If you want to get an excellence, there's several things I need to see. The first off is that you need to get the exact right molecule. So both of these molecules fit the parameters, but this one is the correct answer. And I'll say the merit fits parameters, but not fragments. Guidelines, but not fragment. So let me show you what I mean. So one of the things that we need to think about is what's unique about the fragment pattern that you would see in one but not see in the other. So when I look at this one here, what makes the difference is where that nitrogen is. So if, for example, I cut it off here, I should be able to see a 30 fragment. And if I do 73 minus 30, I should be able to see a 43 fragment as my two combinations. And what I notice here is that 30 is quite low, and when I go look at 43, it's also quite low. So what that tells me is that these are not common fragments. If I want to look for a unique fragment with the 2 amino, I can divide it right here, because I know this guy can't manage to do that combination of CH3 with that. Because if I do that cutoff, you see how it has one less hydrogen? Does it? No, it doesn't. Sorry, my bad. You can cut it off here and it will be the same. Sorry, this one here, there's no way you can cut it off so you get 40 and 43. Sorry, 30 and 43. Do you see what I'm saying there? Because, like, that's the only option. So, if I cut it off here, I would have 14, 2, 12, another 1, and then a 15. So I should get, this fragment is 44, and then if I do 73 minus 44, I should have a 29. Yeah? And we see what the base peak is that 44. So it suggests that this is the fragment. So the thing to remember about these molecules is that they will commonly fragment where the functional group is. So since this is on carbon number 2, I'm going to expect it to split between carbon 2 and 3. If it's on carbon number 1, I would expect the fragment pattern to be cutting off from carbon number 1. Now this first molecule can form a 44 and 29 because it can cut right here, but the thing is it's less likely to cut there. And what I can do is I can show you guys the spectrum data online so you guys can see them both side by side. Anyway, I'll finish talking about what the requirements are for the assessment, and then I'll show you guys, or do you want to see the fragments now to kind of make sure you understand that? Should I see? Okay. So unfortunately this won't be in the recording because I recorded the document camera and not the screen, but what I'll do is I'll still open it up and I'll put the link on Google Classroom for this website because this website is really useful if you want to double check your work or if you are debating between two molecules. So what I'm going to enter here is my molecular formula, and I think I've actually done this one. So we're doing C4H, how many H's were there in there? Is that 9, 10, 11? And then 1 nitrogen. So I can search these guys up, and what I was debating between is the primary, the butylamine, and the secondary butylamine, which is very annoying that its naming is not the way we name things. All right, so this is the fragment pattern if the amine was on carbon number 1. And you see how it has the base peak at 30. Which makes sense because you're assuming it's going to cut where the function group is. If the functional group is on carbon number 2, it's going to cut on that second carbon. So this is the spectra that we were looking at, and you see how its base peak is 44. And that's because it's cutting at carbon 2. And so that's why that fragmentation pattern is really important for the excellence, is you need to be able to identify which of the two choices there are, because both options fit. So they both have the same molecular ion. They both have the same CMMR. They both have the same IR as well. You could use the CMMR as part of your explanation, because if it was, in fact, on carbon 1, we would expect to see that clustering. But even then, it's still, both of them are very similar. So I can pull both of the IRs up if you want to see them. Or not IR, CMMRs. But they're quite similar. So this one here is the amine on carbon number 2. And this, whoa, where'd you go? Come back. There we are. What? Okay, I agree. Oh, never mind. I'm just going to open it up on here. Why are you doing that? CMMR. Yes, disclaimer. Accept it, or you want that one. You want that one. There you go. You see, it's actually like kind of, this one looks more like it's, yeah, that's what I thought when I saw it too. Yeah, this looks more like you would expect it for if it was on carbon 2, and that's why I didn't give you guys the data, because I was like, so that's why I'm saying the CMMR, like, it's not as reliable. That's why we go look at the mass spec. The mass spec would be very clear. Yeah, it is a weird one. But does that make sense to the difference? All right, I'll go back to the document camera. All right, so when it comes to this then, what I want to see then is some justification. So it's actually probably easier when you notice it to then go, oh, I can explain the base peak now. So this base peak is actually that 44. So that's going to be the CH, CH3, and then the NH2. And that's a positive one, and that's going to be your 44 mass to charge ratio. And then the loss component is your CH3, CH2. And that was going to be your 29. Yeah, I lost that from my main molecule, because this is the main molecule, and that's where it cut. This is the charged component. That's the uncharged component. All right, so for the excellence, you need to get the right molecule. That's a given. And you're doing that based off the fragment patterns. The other thing I need to see for the excellence is that process of elimination. So a merit level student will just give me the answer. An excellence level student will tell me what it's not. So for example, an excellence level student will tell me this one is not the correct answer because it only has 2 carbon environments. This one is not the right answer because you'd expect the base peak to be 30. Does that make sense? All right, so for the excellence, I need to see more layers to your answer. The other thing that I'm looking for excellence is that integration of the spectra, so making sure the spectra back each other up. So for example, I would see that this is an odd number. It confirms the nitrogen. So odd number confirms nitrogen seen in IR. So that's now me tying the spectras together. When I'm looking up here, I can tie these two together. So I can write down that this here backs up IR data. Actually, I should say has the CN. Okay? So for the excellence, I need to see that linking of the spectras. Cool, and that's all you need to do. So for this assessment, I'm happy if you guys just annotate on the spectras. You don't need to write a whole lot. So long as I can see your process on the spectras, you're fine. And this acts as your justification. Okay? Any questions? All right.